Hi, this is Pat Hindle with Microwave Journal. Welcome to this new series of online events called RF and Microwave Summits, and this one is focusing on AI and RF. We have another summit taking place November 13th on radar technology, so keep an eye out for that one. In today's summit, we will cover how AI is being used in simulation and design of RF components and devices. We have four great talks today from Rapid RF, Cadence, Keysight, and MathWorks, followed by a great panel discussion on AI, including questions from the audience, so please stay around for that one. Our first talk is the world's first AI RFIC designer from specs to tape out with one click, given by Edward Heidebrecht, CTO and co-founder of Rapid RF. Edward leads the development of state-of-the-art solutions for AI-driven designs of RF integrated circuits. Prior to Rapid RF, Edward worked as an RFIC design engineer at RWTH Aachen University in Germany, where he also received his PhD. His research is focused on novel RFIC architectures, including innovations in integrated Doherty power amplifiers and automations of RFIC circuit design. At Rapid RF, he is driving the transformation of RFIC design to significantly reduce time, lower costs, and increase reliability of manufactured circuits through AI-driven automation. Now I will turn the session over to Edward.
Hello everyone, my name is Edward Heidebrecht. I'm the CTO and one of the co-founders of Rapid RF. Before we start with our session, I would like to thank the Microwave Journal for inviting Rapid RF to the RF and Microwave Summit AI in RF. I am pleased to represent our company Rapid RF at this summit. During the session, I will talk about the world's first AI RFIC designer, which can deliver tape-out ready RFIC designs based on your specifications with a single click. If you work in the RF industry and would like to test our AI platform, you can do so by registering via this link. I would like to start with the question, why do we actually need AI in RFIC design? In RFIC development, we are dealing with a decades-long dilemma of balancing cost, time, and performance. But what are the major challenges in RFIC design? The RFIC design process itself takes several weeks to months without any guarantee of success. In this context, the designer's level of experience has a significant impact on the success rate. RFIC designs has many hidden pitfalls that can lead to unwanted oscillations or early failure of the circuits. Both also lead to high overall design costs of RFIC products. The cost of custom IC development can be up to $250,000 in non-recurring engineering. All of this is further aggravated by the fact that the industry is facing an increasing talent shortage of experienced designers. Since a decade, the enrollment rates in electrical engineering are declining, and the baby boomer generation with lots of experienced engineers are retiring. Due to all of this, the overall RF system development is strongly dictated by the available commercial off-the-shelf components. This is not entirely bad, as it allows for immediate system development and lower overall development costs. But this comes with the price of lower flexibility and therefore high performance trade-offs. Furthermore, there's a strong supplier dependency, meaning whenever a chip is out of stock or obsolete, the developed system must therefore be re-engineered with other off-the-shelf components. On the other hand, custom RFIC part development would provide maximum flexibility, leading to the highest possible performance. Furthermore, it would also lead to full control and independence. We recognize the high demands for custom RFICs in the market, but this could not be realized due to the time-consuming and costly development process. Market analyses also confirm the stated problems. This year, the projected market for RFIC design work is already estimated at 3 billion US dollar, and it is anticipated that this figure will almost double by the end of 2030. Market research has also revealed that the talent shortage is having a significant impact on this area, with many positions remaining unfilled. By 2030, it is estimated that 60% of all new engineering positions remain unfilled, risking the projected market growth. So let's take a closer look at how AI can be leveraged to overcome the challenges of RFIC design. As already mentioned, the RFIC design process is time consuming. Even an expert level design engineer needs at least 3 weeks to finish a layout for an LNA or a driver amplifier. Designing a high power millimeter wave amplifier takes at least 2 months. To reach these timescales as a design engineer, at least 3 years of pure design experience is needed. This is where Rapid RF comes in. It enables RFIC design without any prior expertise, which mitigates the talent shortage in the long term. Our solution is an entire AI-driven design automation, providing tape-out-ready RFICs within less than an hour. For that, also no manual engineering effort is required, and all of that is already proven successfully for various RFIC technologies. So, how does all of that work? And how can a customer get his RFIC circuit? On our platform, you can put in your specifications for an amplifier for the supported semiconductor technologies. With a single click, an AI agent takes over the request and starts designing the circuit for you. Our platform leverages a self-developed AI which automates RFIC design. By combining intelligent design exploration with ultra-fast predictive simulation, it enables optimization and innovation at speeds several orders of magnitudes faster than traditional approaches. This unlocks broader design space exploration, rapid iteration, and self-improving workflows. At the end, you can check the design report and download the tape-out-ready design files for your RFIC. As already mentioned, self-learning and improvement are key elements of our development process. We already have a constant growing database of thousands of fully functional RFIC designs in various technologies. The design generation is constantly improving through extensive space exploration. This technology and approach will form the basis for generating arbitrary circuits in the future, including switches, VCOs, filters, and more complex overall architectures. We for sure recognize the high standards of reliability and trustworthiness demanded by the RF industry. Therefore, our solutions provide expert level designs that can be easily interpreted by RF engineers, as shown in this example circuit here. They can also be verified with conventional EDA software if required. Stability and reliability checks are an integral part of the design generation process. This ensures that the designs are functional and tape-out ready. All of this makes the design process for custom RFICs really simple. You enter your target specifications and let the AI do your design. You retrieve the comprehensive design reports and files, from which you can also do your final checks and verifications if you like, or even do individual adjustments. Finally, you can submit the circuit for tape-out. This increases productivity by over 100 times. I know this all sounds too good to be true, but we have already demonstrated this approach multiple times. In mid 2024, as a part of a deep collaboration with Miller MMIC, we benchmarked our artificial designer against a human expert to demonstrate the increase in productivity. This circuit here on the left side was generated and finalized within a single day. The result is that RapidRF was able to outperform the human designer not only in terms of a 10 times productivity improvement at that time, but also in terms of major performance specifications. The shown circuit is a wideband LNA working from 10 to 20 GHz. It not only outperforms the reference design in terms of gain and noise figure, it also achieves a higher operational bandwidth. Our major goal is to achieve first-time right performance with any generated circuit. Therefore, the predicted circuit performance needs to align as good as possible to the measurement. For that, we did several validations for different circuit types and technologies. By March 2025, Miller MMIC had already achieved the ability to design RFICs within a few hours using the RapidRF design platform. This represented a significant productivity improvement compared to the previous year. The two highlighted example circuits were taped out in 150 nanometer gallium arsenide technology from WIN Semiconductors. The K-band driver amplifier operates at frequencies between 17 and 28 GHz with an output power of 18 dBm, while the Q-band driver amplifier is a 5-stage design that operates at high gain between 32 and 52 GHz, which is exceptional for the chosen technology node. Of course, our endeavors are not limited to linear amplifiers and just increasing the speed of design generation. Our goal is to enable the AI-driven design automation of the most complex RFIC architectures, such as millimeter wave high-power amplifiers, and to enable the design generation for all possible semiconductor technologies. At the beginning of this year, we taped out our first AI-generated high-power amplifiers using UMS 150 nanometer gallium nitride technology. Both the K-band HPA from 17 to 21 GHz and the Ka-band HPA from 27 to 32 GHz achieve cutting-edge performance with a measured power added efficiency of over 30% and an output power of up to 42 dBm of output power. The simulated results show again a good agreement with the measurement result in here. In June of this year, we exhibited at the IMS 2025 in San Francisco, where we launched our AI platform and made our technology accessible to a wider customer base. During the exhibition, we gave extensive live demonstrations of AI-driven design generation. This was all possible because the AI could now perform end-to-end design generation in just half an hour. Currently, LNAs and drivers in MMIC gallium arsenide technologies are available to our customers on the RapidRF platform. Other technologies and circuit types, such as the generation of high-power amplifiers, are currently in the testing phase and will be released in the near future. On the semiconductor technology side, for the general access at the RapidRF platform, the 150 nanometer gallium arsenide technologies of WIN Semiconductors are already supported, and UMS gallium arsenide technologies will also be supported soon. By end of this year, the platform will also offer gallium nitride technologies of both foundries. Furthermore, we support customer-specific non-public technologies to which access is restricted to the owning company. Customers in multiple industries benefit from AI-driven RFIC design automation. And application customers, such as RF system suppliers, can focus on performance-driven development and reduce dependencies. Semiconductor companies are less impacted by the talent shortages. They can design faster and increase their overall success rate. Foundries will benefit from lower barriers to entry for their technologies, reduced technology support costs, and the ability to perform rapid technology benchmarking for new processes. The industry today is largely focused on building what you could call the Swiss Army knife of RFICs. The goal is to design components that cover as many frequency bands as possible in order to maximize market reach and reduce the need for developing multiple separate solutions. This approach is totally understandable, as fewer components mean lower development effort and shorter time to market. However, there's a significant downside. By trying to cover every frequency band with a single solution, designers are forced into performance trade-offs. The result is that no single band is truly optimized. If components were instead tailored to address specific frequency bands, the need for such compromises would be greatly reduced, and the achievable performance per band would be much higher. Naturally, some applications do require these large bandwidths, but in most cases, tailored solutions focused on specific frequency bands can deliver far better performance without the compromise of an one-size-fits-all design. Let's take a look at an RFIC reference on the market. The table and graph show the performance of a 6 to 18 GHz off-the-shelf LNA MMIC developed using gallium arsenide MMIC technology. This design covers multiple frequency bands, including the C, X, and Ku band, which are used for different applications in radar, satellite communications, and wireless communications. And please don't get me wrong, RapidRF is certainly able to build these high bandwidths. For example, this 6 to 18 GHz design was generated in under an hour and offers competitive performance in terms of gain, linearity, and noise figure. But what would happen if we generated the circuits specifically for the mentioned frequency bands? This C-band design was generated in roughly half an hour. With these two stages instead of three, it achieves a higher performance, occupies less chip area, and most importantly, has a lower overall noise figure than the reference design. The same applies to the X-band. This design was also generated in half an hour. With two stages, it achieves 26 dB gain and again, a better noise figure than the reference wideband design. And finally, the Ku band. This three-stage design was generated in half an hour and outperforms the reference design again in terms of noise figure and linearity. As demonstrated, it is extremely easy to generate RFICs with RapidRF that are tailored to particular requirements. Not only can the performance of a given frequency band be improved, but the number of stages required and, consequently, the chip size can also be drastically reduced. This leads to much higher number of chips per wafer and consequently a higher yield. RapidRF is constantly improving its AI-driven design automation. Our vision is an artificial engineer that can support our customers in developing the perfect solution to a given problem. This includes selecting the most suitable architecture for a given task. For example, the necessity of a distributed amplifier for ultra-high bandwidth, or a Doherty amplifier for high efficiency, as well as selecting the most suitable semiconductor technology node. Furthermore, we are working on collaborations to enable the delivery of custom RFIC designs to end application customers. This includes providing a complete service from tape-out to back-end service like packaging to make it as easy as possible for customers to receive their custom chip designs. Our goal is to enable human AI collaborative development, allowing RFIC engineers to focus on innovative architectures and approaches. Ultimately, the AI will assist in the development of entire RF systems. RapidRF is already working on laying the foundations to achieve these goals. RapidRF also has a clear roadmap for its technical services. At the beginning of this year, we worked with our first pilot customers, and by mid 2025, we had opened the platform to a wider customer base for AI-driven RFIC design. Currently, our platform is open to anyone working in the RF industry or involved in RFIC design or planning to be in the future. By the end of this year, we plan to launch public access to gallium nitride technologies for wind semiconductor and UMS, as well as the capability for AI-driven power amplifier generation. By the end of 2026, we aim to empower our customers to integrate their custom technologies into the AI themselves, making this technology accessible to all professionals in the RF industry. Furthermore, our goal is to provide the design automation for every component necessary for full RF front-end development, such as switches and filters and VCOs. We are RapidRF, and we are transforming RFIC design with AI. As already mentioned, if you're working in the RF industry and want to leverage AI for your RFIC design, you can try out on our platform at rapidrf.ai. We will also be exhibiting at the European Microwave Week in Utrecht, the Netherlands, from 23rd to 25th of September. Please visit us there at our booth at number E34, where we will be also doing live demonstrations of our AI design automation. For further information, please also visit our website rapidrf.ai or email us at info@rapidrf.ai. Thank you very much for your attention, and we hope to see you at the next convention.
Speaking of AI, Microwave Journal has added an AI search to our website. You can get expert verified answers to your toughest microwave engineering questions powered by AI using our trusted content from Microwave Journal. The new AI search tool allows you to use natural language queries on microwavejournal.com to get answers to your technical questions about design, simulation, test and measurement, market trends, and more. Since it only uses Microwave Journal vetted content, you know that the answers will be accurate. To use the AI search, just go to the home page and click on Try Our AI Search. You'll come to the page, then enter your question into the query box. How do I design a dipole antenna? Click Ask, and it will generate an answer from Microwave Journal content only. And here we are, the answer to how to design a dipole antenna, including references to all the content that it used. So check it out today. Hi, this is Pat Hindle from Microwave Journal. Our next talk in the RF Microwave Summit on AI and RF is Bringing AI to RF Production Design Flows, given by Michael Thompson, Distinguished Engineer in the Virtuoso R&D Group at Cadence Design Systems. Before we begin, just a few logistical items. If you'd like to download the presentation slides for reference, you'll find them in the handouts window. This presentation is being recorded, so it'll be available to watch later on and recommended to colleagues who aren't able to join us today. Please hold your questions until the panel session at the end of the summit. Michael Thompson is a distinguished engineer in the Virtuoso R&D Group at Cadence Design Systems. His current charter is a development of design solutions for heterogeneous integration across digital, analog, and high-frequency domains. These solutions require complete flows, allowing initial design concepts through detailed design and analysis, verification, manufacturability, and tape-out. He works closely with software developers, end users, and foundries to implement complete deployable development flows. Before joining Cadence, Michael has various roles at Keysight, Agilent, HP, Soft Field Organization. He has a BSECE and MSEE from Cal Poly and postgrad work at USC. Now I will turn the presentation over to Michael.
Hello, and thank you for attending today. My name is Michael Thompson, and I'm part of the Virtuoso R&D group within Cadence. And today I'm going to be talking about our artificial intelligence solutions that we've been developing, but specifically how they apply to RF and also analog production design flows. My presentation is broken up into two sections. The first being how we're bringing the overall infrastructure together that allows us to design a complete system, and how we're bringing those tools into one platform, integrating them together, and then how we're applying machine learning and artificial intelligence applications on top of that platform to aid the designer in early on design all the way through verification and production. We'll discuss what we've done so far and some of the directions of the roadmap areas we're heading towards. Cadence has a long history in the artificial intelligence area. We've been researching it, developing different solutions for well over a decade, with our first industry production solution coming in 2021 with the release of Cerebrus, specifically focused at SoC, system on a chip type design, where we're trying to improve PPA as well as productivity. This pioneering work continues to be leveraged across other platforms as we develop different solutions for different product lines or different areas of electrical design. So we'll start by talking about the infrastructure work that we've already done and continue to work on to build the single integrated platform for design that allows us to then overlay our machine learning and artificial intelligence applications on top of. Cadence has a very large user base that trusts and uses Virtuoso and other products to routinely design their RF and analog circuits. And so when we started our artificial intelligence journey and how we should start developing solutions for this community, we certainly went to them to get their feedback. Optimization is a very important piece that came back to us, that we really need additional optimization techniques, additional optimization flows. So beyond our existing optimization techniques, you're going to see more machine learning or artificial intelligence applications that we started with, but also layout. Getting to layout early and quickly is an area where productivity can be dramatically improved if we can get to those first layout faster and understand some of the pre-layout parasitics. So we've put a lot of work into looking at layout synthesis. And then obviously, since Virtuoso and Cadence is a platform for designing and building going into tape out, we look at assisted sign-off areas, and then how do we improve productivity, allow more design or more simulation to be done more quickly and to be done more completely prior to going to production. Coupled with the user community feedback, we look at what are the trends going on within industry itself, and certainly artificial intelligence is a big one. But beyond that, we see electrifying everything. So being able to look at designs that go into a variety or many different products and have many different use models, being able to continue to expand electrical design that meets Moore's law, even if we're doing it more with a packaging type innovation and not so much on the process itself, but also looking at those foundry investments, foundry improvements, and increased system content along with new areas of exploration such as quantum computing and photonics designs. All of these are taken into account or part of our mechanism for deciding what we're going to work on and how we're going to implement these tools. So with our release of Virtuoso 25.1 this year in June, we took these feedbacks from our user community as well as industry trends, and we focused on some very specific areas. Certainly the artificial intelligence that we're talking about today was one of those. But RF and microwave, as we'll discuss, is also a very important area we've put a lot of effort into. And that is part of our build-up to turn Virtuoso into a heterogeneous integration platform, to be able to do more automation and migration, to move quicker, larger systems, more important parts of the overall system, to improve verification throughput, and to get beyond sign-off and into verification. So one of our biggest infrastructure architectural changes is to bring the Microwave Office platform onto Linux. And since we're bringing it under the Virtuoso envelope, the Linux version will be known as Virtuoso Studio RF. This is native Linux implementation of the Microwave Office design system, and it allows us to work on a common platform between it and Virtuoso. In our first implementation, we have a couple of different methodologies to work between the two different platforms. The first being able to move designs from the Virtuoso RF Studio into Virtuoso, or vice versa, being able to take designs out of Virtuoso and send them into the Virtuoso RF Studio. So I can move back and forth between the two platforms. This is the starting point at tying these two platforms closer together and more tightly integrating them. Along with moving the Virtuoso Studio or building Virtuoso Studio on Linux, you'll see that we've implemented many of the verification and analysis and simulation engines also within the Virtuoso Studio environment, with the idea of being common analysis, verification, and simulation tools across both platforms, and ultimately the exact same capabilities within both tools. In the first method, we're looking at moving designs from Virtuoso into Virtuoso Studio. So we're looking at what we're calling the Virtuoso Design Link that allows us to take designs existing within the ADE environment and migrate them into Virtuoso Studio RF, where we can take advantage of more of the RF microwave type simulation capabilities within that platform to exercise those designs that may have been developed within Virtuoso directly, but then also to combine it with elements that would more natively be designed within the Virtuoso RF Studio or more of a microwave design environment. Here I can bring the two together and run different types of simulations depending upon the application I'm looking at. So the other path is to be able to bring designs developed in the Virtuoso Studio RF or the RF environment into Virtuoso. To that end, we've done a couple different things to facilitate this. One is Virtuoso Studio RF, as well as the Microwave Office product as well, understands Virtuoso Silicon PDKs, so we can design directly in silicon within this environment and move those designs over. Maybe I'm designing a SOI switch, and I want to be able to design it in a more of a microwave environment, but then obviously use it in a higher level system within Virtuoso. I can move those over based on the silicon PDK, but I can also take advantage of more traditional 3.5 gas GaN kits within the Microwave Office or Virtuoso Studio RF environment and move those designs in as well. This allows me to get to develop more RF microwave type components or millimeter wave components within a focused RF tool and still leverage them into larger environments or larger systems that have analog components or even digital components along with it. So I'm sure you can see as we've moved the Microwave Office product onto the Linux platform with Virtuoso Studio RF and being able to consume Virtuoso Silicon PDKs within that environment, that we've moved the two platforms closer together to closer to being sort of a single platform. And over time, you're going to see the simulation engines, you're going to see the environments come closer and closer together along with similar analysis and verification tools. So the longer term vision is to bring these together so they're seamless products and all the capabilities of both tools are available in one environment. We believe this integration of bringing in the RF environment into Virtuoso will give you a much more comprehensive heterogeneous integration environment, but more and more capabilities are being put into these systems. So we also are developing links that get us into our Allegro X products. So we're able to look at different types of packaging and boards that we may want to combine with our ICs, as well as Integrity and Innovis. So if we want to do very large scale system planning or integrate digital portions within our simulation, we're able to do that, all within a common heterogeneous integration platform that brings to bear all the different types of analysis, LVS, DRC, and verification engines needed to get my overall system to production and all the individual pieces verified and also into tape out. So we think we're well on our way in building that comprehensive heterogeneous integration solution for RF and analog with digital content design with what we've done so far. So now let's take a look at the artificial intelligence or machine learning applications that we've layered on top of this flow and see where we're headed. So in beginning our development of AI applications for the Virtuoso environment, we first looked at where are we going to maintain all this different data that we're going to be generating, all of our different models, our retrieval augmented generation for LLMs, different types of simulation data, if we develop specific APIs, compute capabilities, where can we put them that we can leverage across multiple platforms so that if I do want to take some of this design work into, say, Innovis, it's available. To that end, Cadence has developed what they're calling the Joint Enterprise Data and AI Platform, JEDI, and our tools all use this as a common platform for maintaining data and maintaining traceability. On top of that, we started with our level 1, or the optimization that we've mentioned earlier, adding artificial intelligence applications, and we'll discuss that more in future slides. But that was one of the first big thrusts because of the importance to the current design community. But then also as we see more and more of these AI agents appearing, they will prove of great benefit to RF and analog designers in these environments. And we have a couple different layers where we're starting with a conversational type LLM that we'll talk about, more of a help type LLM, but then moving into more complex reasoning where it can actually develop and follow through on different tasks we may give it. And then working our way into an agentic workflows where we're now asking the AI agents to make some decisions, to make some design choices for us and to help us improve the design aspect of the production cycle. And then moving on to level 5 at some point where we will be able to give it some ideas of what we want to design and let it go through all these different levels of design automation, developing a complete design that the AI agent comes back with as a possible candidate for what we want to do in our system. So let's start with level 1, the optimization and layout automation. So Cadence has done considerable organic type growth, internal company growth within both the optimization and layout optimization and generation areas. But there were two leading companies in these two different areas that we were fortunate to acquire. The one being Muneda, which brings in the Wicked Optimizer that allows us for different types of AI applications or ML applications within the optimization area, and also the Pulsic company that has Anime that allows us to generate and optimize different types of layouts and look at different trade-offs, be able to trade off different configurations of layouts. So before we optimize, we're obviously going to need a design to optimize with. So we can either start from scratch in our design, or in many cases, what our designers want to do is be able to map or migrate an existing design from one process node to another, or from a previous implementation somewhere. And to that end, we have a few different ways of doing that. One that we developed is a file-based spreadsheet approach, where I'm mapping device to device, and I'm just running the migration tool from one process to the next. I can do that through a spreadsheet type application, or I can use it in a graphical mode, where I'm actually using the UI to create these mapping techniques. Or more efficiently is to allow the AI tool to do that for me. So we're developing an AI tool that allows us to map from one process node to the next. These are the three different approaches we currently have. And this gives us our starting point. After we've mapped and moved the design, we obviously have to optimize it to recenter the design so that it is now meeting our performance requirements. With larger, more complex designs, as we're using artificial intelligence applications to optimize or recenter these designs, there's an awful lot of data that's being processed and being collected. And since this is too much data usually for a user to be able to review and comment on, we've developed techniques where we can use our smart waveform capability to group different waveforms, to look at quality of those waveforms, to do some sort of understanding of how the design is being extracted and being modeled, and then how we can compensate or get it back to the area that we want for our design needs, so we're meeting our different design specs. With our design either migrated or built within the ADE environment, and with our metrics and being able to monitor the design as we're optimizing it more thoroughly, we can now apply some of the Monada or wicked optimization engines, particularly things like the deterministic nominal optimization procedure that allows us to optimize more quickly and efficiently on larger designs, and recenter those designs, as well as using statistical worst case type analysis simulations or optimizations as well within this environment. These are all being integrated within the Virtuoso environment now in an early beta phase, but will be released in ISR3 at the end of Q3 this year. And as our AI agent is migrating or optimizing this design from a circuit simulation standpoint, we're applying different types of machine learning algorithms, as well as some user-defined structure capabilities to look at the design itself and to actually break that design out into different functionality pieces. So we can actually identify different types of circuit structures, and we can understand how they're contributing to the design itself. And this gives us some starting point on how we may want to lay out this IC or this design. So that understanding of the circuit, what is actually in the design, allows us to do some very early, quick pre-layout type flows where we can start to get some upfront parasitics and circuit sizings early in the design cycle, so I can start to get some idea of what the physical effects are going to be, so that I can start to compensate for them, and then work into a complete post-layout flow where I'm optimizing with complete physical effects, either through parasitic extraction or EM work. I can optimize the final solution, but the pre-layout flow helps me get closer to that final layout and final design goals, and improves the efficiency of my flow. So with an understanding of the functionality of the circuit and being able to do some device sizing, we can start to understand some of the parasitics that we're going to encounter when we do our detailed physical layout. So we can start to include those parasitics earlier in the optimization cycle and earlier in the centering and the statistical understanding of the overall design, and how we can more quickly get to final solution because we're closer to that solution earlier on in the design cycle. Understanding of the circuit and some of our device sizes, we're now able to engage the PulseIC technology to start to evaluate some or generate some prototype layouts for us that we can actually do parasitic extraction on or do EM extraction. And we can now start to include more physical effects in that optimization design cycle. So we can look at various candidates, decide what may or may not be more applicable for our system or for the specifications we want to meet, and start to look at those pre-layout parasitics or effects early on, again, getting us closer to the final design earlier in the design cycle. So here's an idea of how that capability is going to work. Again, this is in our ISR3 release at the end of Q3, where we now have some understanding of the functionality of the circuit using the anime capability or technology from the PulseIC company. We're able to generate various layouts, prototype different layout capability or layout configurations based on the circuit topologies and circuit descriptions. So if I'm looking for more of a tall, thin design or a short, wider design, Anime is going to produce different candidates for me. I can expand on those and iterate on top of them to get something that looks more like what I think I'm going to be using in my final design, and therefore start to get some of those parasitics included in the early on design cycle. And the designer is involved in the entire process. So whether you want to start early on and look at different draft placements, this alone can help speed up your productivity. But then if you want to look beyond placement alone and start doing routing, or then routing and prototyping of what the final design would look like in different configurations, all those different levels are available to the designer and allow you to more quickly get to that final design. And with a good high quality layout understanding, we're now able to start to include those layout parasitics or physical effects back into the overall optimization and design centering of the final schematic or final design, so we can get to our final verified, taped out, ready to go design. So beyond improving the design flow itself and becoming more efficient and more productive, we're looking at other things that will help the designer's environment. And to this end, we have an analog RF assistant that we talked about in levels 2, where we're looking at LLM applications for level 2 and 3. So let's discuss what we've done in this arena. Remembering that our first level sort of LLM is a conversational style or asking questions, moving on to the level 3, which is a more complex reasoning type of LLM. So the first part is this conversational LLM, where I essentially have a help agent that allows me to, or will go and search documents for me, whether it's documentation, app notes, the different rapid adoption kits that we supply, our troubleshooting documents, and develop answers for me there. I can also include my own documents within this, proprietary to remain within a specific company or specific environment, so those documents can be searched, and the LLM can put together a comprehensive answer based on many different sources of data. This is the level 2 or the conversational level LLM. Or the complex reasoning model now gets into more of developing things for you. An example of this might be, I want to generate some skill functions. I want to be able to do something that's not necessarily implemented in the GUI, but I can ask the LLM to build me a skill script that will do customization work for me or custom work within my environment. And the analog RF assistant will go off and develop that skill through a skill agent that looks up different types of, looks up the data within the OA environment, so it knows what the applicable APIs and functions are. It'll build that skill script, refine it, test it, and deliver back a new functionality that may be very unique to what a particular designer is doing, but not something that is generally used enough that it's actually implemented in a broad fashion. So this allows us to do skill function generation, but But beyond that, it could help me set up simulations. So I may ask it, rather than build me a skill script, go off and build me a test bench and allow me to do simulation setup or waveform viewing setup more quickly and efficiently. And here's an example of what that capability might look like, where I'm asking the RF analog assistant to go build me a test bench for a particular type of, say, amplifier simulation. And once it's built me that, and I see that Maestro test bench or Maestro view being generated on the right-hand side, I come back and I think, okay, well, let me point to this particular design. So it actually points to a design that I have built. It'll include that in the Maestro view, and then I'm setting up different parameters or different sweep settings. I can ask it to do those things as well. So rather than me going in and finding the different area within the GUI, clicking on it, setting a parameter, I can ask it to set all these things for me within that view, and it enables a quicker test bench generation and quicker time to simulation, as well as being able to generate the plots or different types of viewing material or tables that I need for my design review. And level 4, where we're just starting to really work, is the agentic design area. This is where that AI agent now makes some judgments, where it's moving between these different areas of the design flow and looking back and forth between layout generation, optimization, and the parameters I have to worry about. And it's doing some additional work where it's not involving the user quite as much, but taking into account these variations and moving back and forth between the different optimization agents, the layout agents, the test bench generation or testing agents, and being able to perform and investigate those designs and improve them prior to returning those to the user. So in reaching the level 4, the agentic workflow, now I have different agents that we're developing for IP cataloging, for generating the schematics or migrating the schematics, sending or optimizing the designs, developing the layouts, extracting the parasitics, working back and forth across these different agents to develop a finalized, migrated or optimized design for you with less user involvement, but being able to do more different types of very finalized designs that I can now trade off between different requirements. So it gives me more time in the design cycle, less time messing with test benches and working back and forth between these different areas manually. So this is currently where we're at with our artificial intelligence solutions, and as you can see where we're headed. Hopefully this has been useful to you, and I really do appreciate your time, and thank you for attending.
Hi, this is Pat Hindle with Microwave Journal. Our next talk in the RF and Microwave Summit on AI and RF is Scalable RF, from devices to end-to-end systems, automation and AI of 3D multiphysics microwave designs, given by Alexander Petter, Senior Director, Keysight EDA. Before we begin, just a few logistical items. If you'd like to download the presentation slides for reference, you'll find them in the handouts window. The presentation is being recorded, so it'll be available to watch later on and recommended to colleagues who weren't able to join us today. Please hold your questions until the panel session at the end of the summit. Alex is Senior Director for Keysight EDA, overseeing the portfolio for RF and microwave, power electronics, and device modeling, while spearheading AI ML initiatives. With a master's degree from TU Dresden in Germany, Alex has a diverse career spanning 3 continents, working in various leadership roles across the foundry, analog mixed signal, RF design, and EDA supply chain. An expert in foundry technologies, metrology measurements, design support, and EDA software development, Alex has recently focused on driving AI ML initiatives at Keysight to enable next generation of AI-enabled circuit design and ML ops solutions. Now I will turn the presentation over to Alex.
Welcome to the RF Microwave Summit 2025. My name is Alexander Peter and I'm Keysight's Senior Director in Keysight EDA, managing AI solutions for RF. Today we're going to discuss key AI challenges in RF, considering the complex stack from device to end-to-end systems that makes RF so unique. While most research and proof of concept focus on RF design automation using AI technologies, I would like to set the focus today on the large picture and what the industry looks like when it comes to AI and RF. To better understand the domain, let's first examine the unique challenges of AI in RF and microwave, followed by the deeper dive into the technologies that are available to address those challenges. At the end of the presentation, I would like to outline what Keysight is working on, what values we are creating, and where we are going to add AI in RF. In today's spirit of AI, I'm going to ask Eric, my AI assist, to present the next slides for today's presentation.
In the past decades, experienced designers have kept using layout tools to create RFIC and MMIC artwork directly. While these tools offer great flexibility, they often lead to irregular structures that complicate verification and testing. Strong IP protections in the semiconductor industry also limit available data, making it difficult to build general foundational models. With manual design processes still being the norm, many of the main challenges for applying AI to RF are related to workforce issues. Building trust in AI is a major challenge before widespread adoption. While proof of concepts for AI and generative RFIC are available, design houses will need to retool, invest in new hardware, and take time to develop confidence in these solutions. A recent survey revealed that over 2/3 of engineers use 6 or more software tools in their workflows, which significantly affects today's productivity. The data shows that 61% of engineers work with 5 to 10 tools, while others use even more, up to over 15. As the number of tools increases, so does the average time spent correlating design and test data, as well as the percentage of time spent on manual tasks. Importantly, 61% of executives recognize that integrating these software tools presents the biggest opportunity to accelerate time to market. The findings underscore the growing complexity of engineering workflows and the critical need for better tool integration to streamline processes and boost productivity. In today's workflows, we particularly face challenges of single-vendor promising solutions that are ultimately not sufficient for a complex end-to-end task for RF design that includes multi-chip technologies, packaging and PCB board integration. Most of the solutions are too limited in their features, not interoperable or point tools to address only certain aspects. To achieve effective AI agentic automation for RF, it's essential to consider today's multi-tool vendor landscape when building AI in RF systems. Effective agentic workflows rely on open tool interfaces and integration layers that allow AI to enhance productivity without alienating existing designers and their preferences. According to Forrest and Sullivan's 2025 Global State of AI report, key factors holding AI adaptation back are human-related, security issues, and lack of investment strategies. While many publications, proof of concepts and first solutions are available, overall AI and ML adoption in RF remains slow. Workflows are deep entrenched. Rethinking and retooling existing design flows will require several iterations before AI becomes standard in RF design. Let us take a look at promising AI directions that can help to accelerate the retooling of RF workflows. The main AI technologies that are going to increase productivity can be grouped into the following domains. Machine learning makes it possible for algorithms and surrogate solutions to accelerate tasks significantly. Large language models boost natural language processing, create better chatbot interactions, and frequently substitute conventional UI and UX with data-driven analysis and prompt-based methodologies. AI agents streamline workflows by combining agent-based strategies with LLMs, machine learning techniques, and various tool APIs for inverse design purposes. Current AI approaches in RF solutions address individual problems and typically function as point tools. Each use case is distinct and often requires specific customization and integration. Developing an AI agentic flow or application involves a significant level of integration. Open APIs are increasingly fundamental for advancements in AI and ML, serving as interfaces that allow AI agents to coordinate workflows and manage platforms. The effectiveness of AI in RF depends on the modularity of tools and the robustness of APIs that facilitate interactivity and integration. Let's take a look at ML technologies that are enabling AI in RF today to improve algorithms, enable simulation speedups and drive the introduction of new agentic solutions. Machine-learned surrogates are a way to take faster, more immediate advantage of your data assets. The first example of how Keysight for years has been applying such surrogate solutions is for measurement-based twinning. This solution enables enhancement or replacement of physical or mathematical-based models with neural network to allow fast and accurate simulations for characterized RF systems. Another application where surrogate solutions have been applied for quite some time are in acceleration of co-simulations, such as circuit and system, or circuit and thermal, where one of the simulations is significantly more complex and requires more time to simulate. Using surrogate for the simulation-intense domain allows creation of up to 1000x faster simulations. You can now do co-design, co-optimization instead of brute force verification. The last is system-level abstractions that are very fast, such as 6G channel modeling, or a PA model can be represented by a neural network to allow fast and accurate system-level simulations. AI agents have rapidly advanced in RF fields, boosting efficiency and supporting agent-driven strategies such as inverse design methods. AI and in particular AI agents are significantly better in managing multidimensional problems. At present, the wide range of states, conditions, and specifications involved in a design closely resembles a comprehensive test plan. Successfully managing these competing trade-offs is a considerable challenge. AI-enabled optimizers have introduced capabilities that did not exist 5 years ago. These tools are now capable of handling significantly larger and more complex problems. Previously, allowing a computer to refine designs was sometimes considered lazy engineering, but this perspective has shifted. Modern design processes require attention to a broad range of frequencies and process variations and temperature profiles. Today, optimizers provide substantial time savings for challenging multidimensional and multiphysics RF simulations. Recent advancements in optimization algorithms leverage breakthroughs in deep and reinforcement learning research. The last area of AI technologies that has been seen as a significant productivity tool for designers in the RF space are large language models. Large language models are rapidly improving, with new and more advanced virtual assistants emerging weekly. RF and microwave technologies are integral to global communication, aerospace, defense, and space. Keysight's virtual assistants, such as chatbots and agents, are built for secure design environments including air-gap infrastructures. The most prominent requirements for RF customers are: 1. Data security. Customers require on-prem solutions due to concerns about external cloud AI leaking IP, which recent high-profile leaks have reinforced. 2. Budget-aware solutions. Providing dedicated GPU resources is crucial since AI applications require specialized computing power, which IT departments are budgeting for now. GPU compute can be quite expensive and the tasks for designing RF systems require specialized solutions. As such, fine-tuned LLM solutions are requested. Keysight virtual assistants use compact, fine-tuned language models for RF tasks, delivering better performance than larger LLMs while optimized for customer requirements and on-prem solutions. Today's topic is AI in RF, though it is not just RFIC or MMIC designs. For an RF company to create an IC, there are many more steps and solutions needed. In today's fast-paced world, getting a functional, verified RF product out to hit a market window is a complex task. How can we achieve this? The use of AI technologies enables faster progress and addresses complex design challenges with increased productivity. Keysight extends solutions beyond the EDA domain by incorporating AI into the physical layers required for RF designs and process and IP data management, offering coverage for all aspects of the digital twin V model. At the center of the V is process and IP data management, which is crucial for any end-to-end workflows. Since AI and ML solutions are all data-driven, owning or structuring your data to enable AI is crucial. Questions that need to be answered go beyond just the AI technology itself. For example, do you even reuse your own data and designs effectively? Do you know what gold nuggets are buried in your own datasets? What is your long-term competitive advantage? If everyone has the same AI tools, how will your company create a sustainable competitive advantage? The answer is probably maximizing your own IP. Which raises a third issue of data security, versioning, and traceability. What exactly is in your AI model, and where did it come from? Do you trust sending your IP to the cloud? Data mining your own IP is a great AI topic. Data and IP management should be in everyone's strategic plan, regardless of which EDA vendor you use. While the majority of AI and machine learning research in RF centers on integrated circuit design, RF engineering actually encompasses a much broader scope. AI for RF needs to address every layer and facilitate agentic flows across various fields. Keysight offers AI-driven solutions across all RF domains, going beyond simple point tools. The Nexus and RF Pro simulators are designed for seamless integration with AI, and ADS allows for comprehensive chip-to-package board design in a single platform, supporting automation and intelligent processes through open APIs and open access compatibility. These technologies streamline autonomous RF workflows and assist in optimizing intricate, multidimensional challenges. 3D integrated circuits or 3D heterogeneous integration is a technology that brings together different types of integrated circuits and packaging methods into a single, compact three-dimensional module. This approach allows RF and microwave IC, packages, and PCBs to be assembled efficiently with advanced tools and co-simulation techniques. 3D heterogeneous integration is critical for RF. It enables the integration of diverse RF technologies, overcoming the limits of traditional ICs. 3DHI reduces interconnect signal loss and improves bandwidth and reliability, key for high-frequency RF performance. It supports streamlined design workflows, allowing the use of a single platform for the entire assembly. This is key for functional, end-to-end systems, not just individual ICs. Co-simulation ensures accurate modeling, resulting in better performance and verification coverage. 3D-HI is essential for next-generation systems like 6G, which demand flexible, high-density integration and adaptability. In short, 3D-HI is transforming RF and microwave design by making systems more integrated, efficient, and ready for future communication technologies. Keysight solutions are designed for such applications. They also support co-designing interposers technologies and integrated passives through 3D electromagnetic, 3DM, and circuit co-simulation, which allows for accurate modeling of RF paths within the 3D-HI structure. This approach supports multi-technology assembly and integration, improving efficiency and performance in complex RF and microwave systems. Modern end-to-end system solutions are needed to allow AI-driven decisions in the assembly process and support drag-and-drop integration of RFICs, MMICs, packages, and PCBs into 3D-HI modules with outcome-focused system-level RF performance verification. Machine learning and optimization can be based on results, like error vector magnitude, coming from many different physical domains. It's important that AI algorithms and agents be able to drive all these directly using APIs, or else you will always reintroduce a human finger into your loop. Keysight simulation tools such as Nexus and RF Pro are vendor-agnostic platforms that support user-driven innovation. The physical layer is changing in RF, AI is baked into the future of the communication standard. 6G is transitioning from fixed, allocated assets to optimized, reconfigurable physical layer. Systems are increasingly autonomous, using advances in AI or ML. RF hardware will need to accommodate dynamic adaptation of frequency, bandwidth, MIMO, and more. The next generation networks have AI baked into the standards. Keysight has tools to simulate those AI-enabled behaviors, the waveforms and fading that they are reacting to, in a way that is 3GPP standards compliant. In addition, Keysight can help you generate the faded waveforms for your training sets. If you're going to create intelligent RF equipment for 6G, you need a dance partner that imitates all the dynamic conditions and transacts with you in a 6G compliant way. Keysight's Wireless Pro is a platform to do that.
In today's presentation, we learned about the challenges that AI faces in the RF space, what technologies are available to continue establishing AI solutions for RF, and what end-to-end RF and microwave solutions really look like. At Keysight, developing AI solution is one of several areas of investment. The promises of AI in RF is to enabling everyone to innovate at their own speed. Accordingly, we are focused on offering AI solutions that customers need, as well as AI-enabled platforms that support agentic workflow creation by all domain experts. So what are the next steps? The goal for all of us is to increase and maximize the productivity we have. There are three vectors which allow us to do this. In recent years, compute, which enabled hyperscalers, allowed us to simulate more and compute more at the same time. Workflow automation keeps allowing us to increase our workflow efficiency. In the future, we will see reasoning and autonomous solutions. The complexity of systems is the third vector. In the past, we looked at individual point solutions to address the space and optimize the solutions. Now we're looking at components and also systems. The overall goal is to maximize the volume we can cover in the space to ultimately arrive at the AI agentic workspace, where we can focus on the what rather than the how to solve problems. With this, we're giving humans the ability to drive more solutions in less time with higher performance and lower overall cost and risk. As AI revolution sweeps across the RF design landscape, EDA vendors continue integrating AI deeper into their portfolio and offer copilots and chatbots as part of their products to enhance productivity. Inverse design solutions are already available for filters, 3D passive, and RFIC designs from multiple EDA vendors. Some EDA vendors are focused on AI enablement by interoperability software that enables through Python API the creation of more agentic workflows in the customer accounts. If you're a designer, you should prepare yourself for AI and RF. By investing in AI technology, learning about the available features and how they can be enabled, that's the guarantee for future career development. Learning Python is a must. Python is the language that AI speaks, and Python APIs are the interfaces that will enable higher productivity and agentic workflows. Similar important is it to understand what end-to-end RF really means. Just focusing on a single domain was enough in the past, but with the connection of multi-physics and higher system level domains, knowing how those interact is important. Individuals who had careers in single domains need to learn what their partners in other domains are doing. If you're the leader in a design house, it is the most important thing to develop an AI strategy. That strategy needs to cover what level of security do you need in your company for your IP? How are you going to manage your data to enable AI to learn from it? And what are the functionalities that will give you the edge over your competition? In addition to those, you also need to understand what kind of hardware you need to be successful, what kind of IT infrastructure and investments are needed to enable all those new capabilities. For this, you should reach out to your EDA vendors and make sure that the developments in their pipelines are matching with your CapEx and OpEx investments. Keysight is a trusted end-to-end solution partner in the RF and microwave domain. Our RF solutions for EDA, test and measurements, and our agentic workflows will help you to stay competitive in the new world where everyone will have higher level of productivity. So before I let you go, please take a look at the resources listed here. To get started with AI for RF, I highly recommend here in the top left to start with Keysight's resource page. It lists Python automation and also AI/ML topics that have been implemented in the past and are available to you. It includes tutorials and also downloads which you can use to get started. In addition, you have 3 more examples here that picture additional presentations from researchers and collaborations we've done in the past. It gives you an idea what's available and what's possible today. So thank you for your time today and best regards for your AI and RF journey.
Hi, I'm Darren McLernan from Keysight EDA, and we're here at the IMS show to show all the latest in EDA software. And this year, we are highlighting a bit more on automation as an on-ramp to AI/ML. There's 3 key things I'd like to just show here at the show. One is that Keysight has detailed Python APIs that we've modularized the guts of ADS. You can drive everything from schematics and layouts and engines and plots, drive it headless and automate your own processes for machine learning and for all the enterprise automation that you want to do. We've been also including a number of newer AI technologies on the insides of our products to make the customer experience of design faster and more convenient, from faster modeling with neural nets and surrogates and co-simulations to a new generation of optimizers that are an order of magnitude faster, as well as a new circuit simulator with APIs that can run headless. We also have chat that's learned all of our tech support articles and manuals to answer questions. Where that's headed, all of these technologies will continue. And with co-pilots, instead of generating English words, they'll eventually generate API calls that you can run, and it will assist you in setting up simulations and doing your daily life. Where that's all headed is in whole environments to do chip design. Here at IMS, you've seen many technical papers about the exciting possibilities with AI. Under the CHIPS Act, NatCast has funded us as the only EDA vendor to do an actual environment to do MMIC design using AI-driven RFIC techniques. So that as that platform comes out, we'll be commercializing the pieces, and you'll eventually end up with the beginnings of AI-driven, a platform to do AI-driven chip design. Today, we're starting with APIs. We're enabling our customers to data mine their own databases, to make their own AI technology, because AI progresses so fast that anything a vendor can give you today will be obsolete in a couple years. It's better for you to control your own destiny and mine your own data securely, no IP leakage, and provide your competitive advantage by mining your own data. So we're enabling those tools. We'll also provide a commercial environment at some point to actually automate that process and really assist what a human engineer can do in any given day. So if you'd like more information, please just consult the keysight.com website for more information. And thanks for coming to the show.
Speaking of AI, Microwave Journal has added an AI search to our website. You can get expert verified answers to your toughest microwave engineering questions powered by AI using our trusted content from Microwave Journal. The new AI search tool allows you to use natural language queries on microwavejournal.com to get answers to your technical questions about design, simulation, test and measurement, market trends, and more. Since it only uses Microwave Journal vetted content, you know that the answers will be accurate. To use the AI search, just go to the home page and click on Try Our AI Search. You'll come to the page, then enter your question into the query box. How do I design a dipole antenna? Click Ask, and it will generate an answer from Microwave Journal content only. And here we are, the answer to how to design a dipole antenna, including references to all the content that it used. So check it out today. Hi, this is Pat Hindle with Microwave Journal. Our next talk in the RF and Microwave Summit on AI and RF is AI-driven antenna analysis and simulation with MATLAB, given by Georgia Zakelli, Product Manager, MathWorks. Before we begin, let me cover a few logistical items. If you'd like to download the presentation slides, you'll find them in the handouts window. Note this presentation is being recorded, so it'll be available to watch later on and recommended to colleagues who weren't able to join us today. Please hold your questions until the panel session at the end of the summit. Georgia is product manager for RF and mixed signal at MathWorks. Before moving to this role in 2013, she was an applications engineer focusing on signal processing and communication systems and specializing in analog simulation. Before joining MathWorks, Georgia worked at NXP Semiconductors on mixed signal verification methodologies and at Philips Research developing system-level models for innovative communication systems. Georgia has a master's degree in electrical engineering and a doctorate in electronics for telecommunications from the University of Bologna. Now I will turn the presentation over to Georgia.
Hello. In this presentation, I'm going to talk about specific problems that every designer faces when dealing with the analysis and simulation of antennas. And I will show you how AI, or artificial intelligence, can practically help you with these problems. This is not going to be a talk about theory or research, and we will see how AI can help you today and in very practical ways. So what are these problems that every designer faces? Electromagnetic analysis is required for antenna design, but it can be very time-consuming, especially when you need to perform it several times, like in an optimization process. Antenna simulation and measurements generate a lot of data that needs to be analyzed, and this data can be incomplete or partial or corrupted. And last, antenna designers might not be familiar with AI tools, so might not be able to easily assess if AI is useful or not. What I'm going to show you next is how MATLAB and AI can help you in addressing these specific problems, and namely with three techniques. With a pre-trained AI antenna catalog object for faster design and analysis compared to electromagnetic analysis techniques, how MATLAB and AI can provide you with a deep learning convolutional neural network that allows you to reconstruct 3D far-field radiation patterns from 2D measurements, and how you find AI-powered optimization techniques for antennas with many design parameters, how you find these techniques in MATLAB for you to use straight away. And last, I will also show you how you can perform antenna analysis, importing measurement data, and performing optimization in the same environment, and then also using these results for system-level simulation. So the first tool in the hand of any antenna designer is electromagnetic analysis. If you're not familiar with MATLAB Antenna Toolbox, well, definitely I invite you to try it. And I want you to make aware that the Antenna Toolbox makes it easier for antennas designers to start with a catalog of antenna elements and several apps. And from this catalog of antennas and from these apps, you can perform full-wave electromagnetic analysis using different techniques. You can also design custom antennas, planar structures, as well as 3D structures, and integrate with RF-PCB toolbox for finite element analysis. And last, you can also integrate your antennas on large platforms and include propagation effects. This is all available to you if you have the MATLAB Antenna Toolbox, and it has been around for, by now, a number of years. But what if you need to explore large design spaces? What if you wonder if AI can help you in speeding up the antenna analysis? How can AI further assist electromagnetic simulation? So the Antenna Toolbox provides pre-trained AI antenna models, and this is really a unique solution. So not only in Antenna Toolbox you find a catalog of antennas that are parameterized in geometry and that you can solve using electromagnetic analysis techniques, but you also find the same objects, actually a subset of this catalog, namely 8 type of patch antennas, waveguides, horn, and different type of dipole antennas that can be analyzed using AI. So you can estimate the resonant frequency, the bandwidth, the beamwidth, and the peak radiation in a fraction of seconds. So in these images that you see here, you see how the electromagnetic analysis, which is already very fast, takes approximately 1300 seconds for 49 design points, while the AI model takes 16 seconds, so really less than a third, for over 2,600 points. So a speed up of 3,000 times or like. And by the way, at the bottom of the slide, you get a few references for additional material that might be helping you. So what I'm showing here is pre-trained objects. You don't have to do anything to train the objects. They are already available for you, and you can use them for rapidly estimating all these properties of the antennas. Here we have an example of a planar inverted F antenna, a PIFA antenna that gets designed to resonate around 2.4 gigahertz. And you can see here that this antenna is parameterized in length and width and height, as well as the short pin width. And with this antenna, you can rapidly estimate the resonance frequency as well as the bandwidth of the antenna. You see how because the antenna is pre-trained using AI, it just takes a fraction of a second. And because of that, we can repeat this operation over and over again by changing the tunable parameters and estimate all possible combinations of height and length for the PIFA antenna, and estimate the resonance frequency and the bandwidth of the antenna. So you can really find all possible, it's essentially a tool for brute force design. And once you find a good candidate for your design, you can simply perform electromagnetic analysis using the same environment, the same tools, the same techniques, and that you are familiar with. And by the way, again, here at the bottom, you find an example where this is implemented. But you might wondering, this is very interesting, this is very helpful, but what if my antenna is not exactly one of these pre-trained antenna models? Maybe I have an antenna that gets reused for different designs, or that I want to provide to a system engineer to perform some exploration analysis rapidly. So in MATLAB, you find tools to train your own AI antenna model. And here we provided the recipe that you can follow step by step. And we also provide you with an example that you can follow. In this case, we have a probe-fed C-shaped microstrip patch antenna that is constructed by cutting a rectangular slot at the radiating edge of a conventional patch antenna. For this antenna, we identify the tunable variables or the predictors for our AI models, as well as what are the desired metrics that we want to use to train our machine learning model. So in this case, there are 5 sets of length, width values, substrate height, dielectric constant that we can change as part of the antenna. And in terms of predictors, we want to estimate the resonant frequency and defined as the operating frequency at which the reflection coefficient or the S11 or the magnitude of S11 is minimum. From here, we can conduct a design of experiments to get a collection of observation for the different design variables sampled within the range of interest. For each length, width set, slot length, slot width, and slot offset, we can look at the possible combinations as well as the combination of the dielectric constant. So we can have a lot of different antenna design parameter sets to analyze. We generate the response using full wave electromagnetic analysis for each parameter set and explore the analysis results over a range of frequencies with a certain given resolution. Before training the model, and this is the time-consuming process because, like as you know, to train an AI model, you need a lot of data, and gathering the data is most of the work that is needed to train these models. It's the most time-consuming effort. Before we train the model, we want, however, to pre-process the data, and we want to effectively make sense of it. So in this case, we want to plot the multivariate relationships that are present in the data. And this is an important step in the machine learning workflow because it helps you in assessing the quality of the collected data and familiarize with the overarching relationship between the different design parameters. Last, out of this data, we actually use 80% for training the model and 20% to validate the model. So we use 80% of this data in MATLAB, and we use the fit-R function, that is one of the available functions out of the box, to find the best model that fits this data. In this case, we use actually a Gaussian process mode of the nonlinear type that gets used to generate an AI model for this antenna. And last, we assess the results against the training data that is perfect and against the remaining data that has not been used to train the model. And what we see is that the AI model performs reasonably well on most test data sets, with the prediction error exceeding 5% only in a handful of observations. So again, you can estimate, you can use a different type of AI models that get automatically optimized on the training data. You can visualize the training data, make sense of it, and then build your AI trained model that you can then share with your colleagues or your customers for design space exploration without the need to perform a long and extensive electromagnetic analysis. So this is a very practical means in which AI models can really be used as a proxy for electromagnetic simulation. Another technical step that is often involved in antenna design consists in dealing with data, importing data, visualizing data, assessing the quality of data, either from electromagnetic analysis or from measurements. If data is in the form of radiation patterns that might be provided by colleagues, customers, or suppliers, well, it's no surprise to you that you can easily import it in MATLAB. It's not exactly rocket science. We have all imported, for example, CSV files in MATLAB. But what might be maybe more interesting for you is to know that you can also import richer file formats such as MSI, Planet, FFS, and FFD. The data can be visualized in the form of structures and objects, and then can be interrogated and visualized without any additional post-processing. You might wonder, this is straightforward. Well, actually, when it comes to electromagnetic data, nothing is easy. Understanding what is the meaning of data, what is the normalization, what is the actual value is actual value in terms of power, voltages, excitations, measurements, metrics, units. It's really not straightforward. Once you have this data imported, you can actually use the measured antenna object as a container, not only for your radiation pattern, but also for your S parameters. Think of it as a single container that can actually absorb a lot of data. For example, for an array, you can have the 3D pattern over multiple XYZ location at different frequency for each antenna element in the array and for the two polarization components. Once you have all this data that comes maybe from third-party tools or from measurements, then you can use it in MATLAB. And you can, for example, interrogate it with functions such as pattern or ENH field or S parameters. And what is interesting is that these functions are the same functions that you can apply to the antenna elements to apply electromagnetic analysis simulation techniques to the actual geometry. In other words, you can swap in and swap out electromagnetic analysis with measured data using exactly the same functions. This, of course, improves efficiency and facilitates comparisons in your workflow, making it simple to identify and debug issues. But so far, no rocket science. Let's now see how AI can actually help in managing data. And in particular, what if you have data that is partial, limited, or corrupted, and you still want to integrate this measured data into the system-level analysis? And what if you have an antenna in the lab and you want to characterize it, measure it, but you only want to do it for a limited number of points because this characterization can be time-consuming? I'm going to take a specific problem that is the problem of pattern reconstruction. So let's say, for example, that you have a partial pattern described with just two cuts, a horizontal and a vertical cut. I'd like to challenge you even mentally. Can you reconstruct the full 3D pattern from the two slices that are now shown here on the screen? This is a very challenging exercise because you need to essentially extrapolate or extend the data through rotation across the entire space. And this is necessary if, for example, you want to integrate this antenna into, just to make an example, a rectangular array, and then enable beam steering or beam forming. By the way, this is a real problem. This can be the case in which you work with antenna data sheets where you only have these two orthogonal cuts, or maybe when you are in the lab and maybe your manipulators for your antenna don't have full degrees of freedom, so you cannot rotate the manipulator around the entire antenna object. So the question is, from these two cuts, can you reconstruct the full antenna far field radiation pattern? There are different techniques for 3D pattern reconstruction. Some are based on analytical methods, and I'm not going to talk about it, but you find these two different analytical methods based on interpolation in MATLAB Antenna Toolbox. What instead I'm going to talk about is a different techniques that is based on AI. And I'm going to talk about it because it actually provides far better results than analytical methods. And one of the advantages of using AI is that you have fewer assumptions on the input data compared to analytical techniques. If you think about it, this is like is not dissimilar from an image reconstruction problem where AI is already and broadly used. So it just makes sense to use AI for this type of problem. So in MATLAB Antenna Toolbox, we have generated lots of antenna patterns. Actually, we generate more than 100,000 unique patterns for single antennas, arrays, and even use the image augmentation techniques such as noise and transformation. We use this data and we generated 2D slices and use these 2D slices as synthetic data to train a convolutional neural network to predict the 3D pattern. Because this is synthetic data, we know what is the ground truth, what is the actual 3D pattern, and we compare it against the reconstructed pattern. The convolutional neural network is trained with an autoencoder that uses a custom loss function that determines the bottlenecks for activations. These activations are triggered when the prediction is further away from reality based on the loss function. The custom loss function, this is really the special sauce that we implemented, uses the absolute error, the structural similarity, and perceptual feature-based loss. Because we have perceptual loss features that capture specific features of the antenna, this guides the process towards a more perceptually similar generated pattern. In other words, not only the reconstructed pattern is close to the ground truth, but it also is closer to the ground truth on the features that really matter for this antenna. Here you see a snapshot of results of a non-conventional antenna. And this is a non-obvious antenna pattern, and obviously a pattern that was not used to train our convolutional neural network. In the middle, you see the 3D pattern. On the bottom, the original results, and on the top, the reconstructed results. And on the right image, you see the difference between the two. And as you can see, the quality of the reconstruction is excellent, not only from a numerical perspective, but also from a perceptual feature-based point of view. And this data was generated using electromagnetic analysis. Here we also see another validation example, this one based on actual measurements, and this comes from a very engaging collaboration with Rodi Schwartz, and I'd like to acknowledge and thank especially Adam Tankelun for his help. In the plots, you see here the comparison between measurements and the AI reconstructed pattern for an extremely wideband EMI antenna that was recently launched by Rodi Schwartz. As you can see, the prediction is excellent. You see the maximum difference at the ports where the pattern scale is really small and the data is a little bit noisy. You can use a pattern from the AI in Antenna Toolbox today. Is a relatively small convolutional neural model, 30 MB, that provides exceptionally high quality results extremely fast, in a fraction of seconds. Again, a great example, practical example, where AI can really be used to solve a specific problem very effectively. Another typical challenging step in antenna design consists in optimizing the antenna performance. In Antenna Toolbox, already for many years, you find the surrogate-based optimization method named SADIA that has been developed in collaboration with Professor Beaulieu from the University of Glasgow. SADIA stands for Surrogate Model Assisted Differential Evolution for Antenna Synthesis, and it essentially utilizes an AI model to learn a subset of the design space as one proceeds along the optimization search curve. A way to think about it is using AI on the fly. While we optimize an antenna, we train a surrogate model of the antenna itself to speed up the optimization. The art of the surrogate model is really on how the design space is sampled in order to create the surface response. There are a bunch of iteration steps. So first, we selected the best candidates designed from a given population. Then we apply differential evolution to generate a number of child solutions. For each child solution, the nearest design sample is used as training data point to construct a local Gaussian process and a surrogate model. And then we carry out electromagnetic analysis to the best child solution, and this simulate candidate design, and this function is added to the database, and the process is iteratively extended. Until what? Until the specifications are met or the objective value does not improve for a certain number of iterations, and then we stop the process. Here you see the example where we applied SADIA for the optimization of a Yagi UDA antenna. And what is interesting is that we compare the performance obtained with the surrogate-based optimization against the datasheet's value of an antenna that has been that is commercially available and that is operating in the same frequencies. What you see is that the values are very similar. This means that not only we found a solution, but we found a solution that is feasible and that makes sense, which is of course very reassuring. We further extended these optimization techniques, if you like to say, by using more AI in order to deal with very large number of design variables to further speed up the antenna optimization and also to allow you using a MATLAB for optimization even when you're using third-party electromagnetic analysis tools. So in the latest MATLAB release, you find the training cost reduced SADIA algorithm that is faster and that uses an adaptive Gaussian process prediction and that can handle many design variables, up to 80. TR-SADIA implements a better trade-off between the accuracy of the surrogate model and the computational resources that are required for its training. And it does so by minimizing the number of training samples and by using an adaptive sampling technique that in a way assures that most of the computational resources are directed towards the most promising regions of the search space. It uses a local search, which is faster, to pushing the optimization ahead quickly, especially during the initial iterations. And then it uses clusters of candidates generated by differential evolution, thus minimizing the number of Gaussian models that are effectively required. And despite the reduced training cost, the RSADIA maintains high optimization accuracy by providing effectively fewer surrogate models and better surrogate models. You can use the TR-SADIA today in MATLAB and Antenna Toolbox. You find it integrated in the apps with standard objective functions, also supporting geometric constraints. And you can use it from the MATLAB command line to define your custom objective function and to integrate with third-party electromagnetic analysis tools. So this is a very powerful tool that again you can use out of the box. Once you have an antenna designed and analyzed, characterized through its measured data and optimized its performance, what can you do with it? Well, what you have to do with it, you might need that you might have to integrate it within, for example, a wireless system, and you might want to simulate the end-to-end performance, or you might need to integrate it on installation platform or maybe propagation environment and active RF front ends. In MATLAB, you can do all of the above. You can integrate the antenna array into active RF systems. You can integrate antennas with installation platforms or large structures, such as parabolic reflectors. You can integrate your antennas inside the propagation environments. Now we also support GPU-enabled ray tracing. You can integrate antennas with a phased array algorithm, analog, digital, or hybrid, and even estimate satellite scenarios, such as links between satellites and terrestrial stations. So you have a single environment for the entire antenna design, analysis, optimization, and system simulation. So I'd like to conclude and bringing it all together. We found 3 practical examples where AI can really help you in accelerating antenna analysis and simulation. By providing a pre-trained AI antenna catalog object, by providing a deep learning convolutional neural network for pattern reconstruction, and AI-powered optimization techniques. And you can do all of this together in the same environment, as well as integrating for system-level simulation. Thank you for your attention. I hope that you find this useful and that you want to try it, how MATLAB Antenna Toolbox helps you in applying artificial intelligence in your antenna design.
So welcome to the panel session portion of the RF and Microwave Summit, AI in RF. So we've just heard from 4 companies on how they're using AI and RF and microwave products. We had great talks. Rapid RF discussed their AI RFIC designer. Cadence discussed how to bring AI to the RF production design flows. Keysight EDA discussed automation and AI of 3D multi-physics microwave designs. And MathWorks talked about AI-driven antenna analysis and simulation. So now we have these 4 experts here on our panel session. We will be taking questions from the audience, so if you have questions, enter it into the Q&A box, and we'll get to as many of them as we can. But to start off, I have a bunch of questions lined up here, so I will kick it off with the first one. Can AI be used effectively for the design space exploration? For example, finding optimal MMIC or antenna layouts faster than traditional methods. And I did see someone kind of have this question. They said, I'm an experienced designer, so what good is AI to me? I know how to do this really quickly. So I just wanted to talk about that. So maybe we could start with Rapid RF. You can discuss the MMIC side, and then we can go to Georgia for the MathWorks, and then anybody else can chime in.
Yeah, thank you. So I think it's certainly possible because it is all a matter of, let's say, providing the right environment for the AI with the appropriate interface. And this interface is basically the language the AI needs to learn. And so in our case, large design space exploration is actually a key element in Rapid RF's approach to teaching the AI on how to build RF circuits. And with that, we have already proven that our AI is actually able to develop and optimize tape-out-ready multi-stage amplifiers in less than half an hour. So certainly this approach works. And this approach is also becoming faster and faster because the AI is also learning from existing knowledge and does not need to do the full investigation anymore. And this enables even more complex systems to be explored later on.
Georgia, how about the antenna side?
Well, it's as always is complicated, but the answer is yes, AI can help. So in my presentation, I talked about these AI antenna objects that are blazingly fast. It takes a fraction of a second to compute the performance of an antenna. There is no electromagnetic analysis that can compete with that. But like for everything in life, there are 2 aspects. There are 2 sides of the same coin. The cost goes into training the AI network. So there is no free lunch. So you need to put intelligence in these AI models so that they can become faster than electromagnetic analysis or measurements or other accurate tools. So the answer is it can work, but there is a cost to it. So it is a tool that has to be used with intelligence. Essentially, you want to create such a network when you have to redesign your component multiple times, for example. A different aspect or a different answer that I could give is, for example, when using a surrogate-based method, surrogate-based optimization. But essentially, as you proceed with an optimization, you build the AI model on the fly. In that way, essentially, you would have to go in any case through an expensive evaluation of the, for example, the electromagnetics results. But the AI model helps you because as you build the surrogate is faster than the EM analysis. So you might wonder what has to do surrogate optimization with design space exploration. That is the original question in your answer, in your original question. Well, when you have essentially very loose boundaries for your optimization. In other words, when you have a very large design space to optimize, and when you can use surrogate-based optimization methods that apply to a global space that are not specific to local solutions, then indeed you can use a surrogate-based optimization as a way to explore the design space exploration. And it can come up with very interesting, very different answers and results that you might expect. So the answer is yes, AI can help, but I think we are still at the early stage. I'm going to give you a long-winded answer, so guys, I apologize. AI can help, but it is like anything else, is a tool, and it is a tool that has still to be used with intelligence from the users, I would say, at least in these early stages. I hope it answers, Pat. What do you think?
I think so. Any other comments?
I would just add here one comment, which is systematic errors in the design process. So we still have to consider that there are systematic errors in the models, which you have to adjust for after you've done the final design, which means for high performance circuits, you have to look into trimming or, refining the solution, which is something which need to be trained into the systems. That means you have to look at even global problems. How good are your models? If you don't know how good your models is, if you have uncertainties in the model and you use those to perform designs, or if you don't know what the systematic errors or the deltas in your simulators are, those systems can predict solutions, which ultimately need to be either trimmed or not functional in the final in the real world. So we also have to be realistic about some of the high performance use cases where systems have been designed with ideal scenarios, which in reality are not functional.
Okay, great. Next question, how is AI changing the traditional workflow of simulation, prototyping, and testing? Maybe we can start that off with Michael.
So the AI's applications are changing that in considerable ways. As I mentioned in my talk, a lot of designs are not start from scratch, clean designs or new designs. They're based upon an existing design. They're based upon existing experience. So being able to have an AI agent that can go out, migrate that design over, get it set up for simulation under the new conditions or with the new process, greatly improves the productivity of a designer and gets them to that first silicon or first gas much quicker. So being able to just have the capability of AI to do some of those mundane tasks, like I mentioned in the talk, being able to generate test benches or setting up simulations, preparing graphs, building stuff for critical design reviews, all those intermediates, all those functional steps that you have to do within a company to get something built, it is going to improve productivity in all those areas.
Anybody else on the workflow?
Well, I think that AI will make us hopefully all a little bit, how can I say, faster in doing the boring things, especially coding and writing code and writing scripts and repetitive tasks. I think that nobody really likes doing that, but we all have to recognize that this is a large part of our job. And I think that AI is already proving to really speed up that aspect of our job. So writing test benches, it works really well. Scripts, data analysis, data cleaning. I mean, it's what I usually call it. It's not rocket science, but it's still stuff that takes a large portion of our time. So that's on the short term something that is definitely happening right now, and hopefully going forward, it will make our simulation faster, or maybe we'll do a little bit fewer simulations that are smarter, in the sense, in the critical cases that really matter. Then we will put all our effort and all our CPUs in GPUs at work. Hopefully it will work also as again, I'm giving a long-winded answer. It will also give us maybe a smarter interpolation tool, if you think about it. Something that will look at the data and will recreate the data like pattern reconstruction. It does a better job than just the classical analytical methods. So I think that this type of tasks we will really see AI contributing really in the short term, in the coming now, pretty much.
Yeah, and so there's some, I might mix in some audience questions here. How does, test and measurement, go into this? It's kind of similar to our question. How do you validate the AI-driven simulations to make sure they're trustworthy? So like in the MMIC, you showed some measured results against the simulations to prove it out. So what role does the test and measurement have in this feedback?
Yeah, maybe I can take that question. So I think it's not just test and measure, but it's also verification, right? So I already mentioned that engineers simplify their problem. That's an engineering discipline we keep using also in simulators to make them faster. Accuracy is a trade-off. So knowing the systematic error of a system is important. There are basically two ways to deal with this. Either you're aware of the systematic error and you build that into your design flow, or you go for verification, which can be either more precision simulations, or you go for test and measure, which requires a tape out at least. So you have to have at least one iteration if you don't get it right in the first iteration to refine it. Or you go for solutions such as trimming. So you can build workflows where you basically embed the test and measurement solution with an intelligent on hardware optimizer, which takes care of the trimming. That optimizer can also be AI enhanced. So similar to what we see in the design domain, you can basically ask an AI, this is my ultimate goal. My input now is the DUT, the device under test. Your hardware provides the feedback loop, and you can ask the optimizer or the AI to basically refine the solution to the point where it hits the target goal. So all of those technologies are very similar. It's just you're adding complexity into the system and you're refining your workflow so that you can counter all the systematic errors you might identify or might have knowingly or unknowingly in your system. And maybe just Georgia mentioned an important point, which is mundane tasks. So that's the feedback we hear a lot from designers. They like to be creative, right? That's what they get paid for. That's what they get hired for. So a lot of times we receive the feedback is don't obsolete the creative portion of the design. Help us to improve our productivity on the mundane tasks. So those are really solutions where workflows kind of have to be milestone based. It's not front to end. You want verification in between. You want to make sure that the designers still have a say in each step and have the opportunity to inject their knowledge where they can help refining the flows and counter early some of the inherent system flaws.
That's actually great. My next question was, how has it been received by customers, both good and bad? So that seems to be a key point of feedback is, reducing time, but not taking the intelligence out of it. Any other comments on customer feedback or test and measurements verification?
Yeah, well, maybe I can add up from our side. So we've got highly positive market response actually. Also, when we launched on the IMS this year, there was quite a lot of interest, and since then, we've got lots of registrations, and particularly from foundries and IDM companies who are very interested. But sure, there's also like the problem or the natural caution and skepticism. And as Alex also mentioned, people don't want or want to put their, let's say, final optimization to something and trying out things. But I think, especially if it comes, for example, for MMIC design, building the interstage networks, I think this is a, let's say, outgrown process. There is not much to optimize anymore. So what we should really focus on is bringing the AI to a point where we can really innovate on more complex architectures, like, for example, complex power amplifiers, millimeter wave power amplifiers, or Doherty amplifiers, something what is really, quite complex and takes a lot of development time naturally, because there are multiple matching network stages involved and whatsoever, which could be automated in, for example, in our case with the RapidRF tool. And yeah, this is basically my side.
Yeah, my experience, it was kind of funny because a few years ago, lots of customers, people were reaching out like, do you do AI? With very broad and open questions. And things have changed nowadays. I think that the questions have become a lot more specific.
Mhm.
And also, I think that on the speaking from MathWorks, from a side, let's say, of a software tool vendor, we also learned to provide the solution to practical problems in a way that in the end, what matters is you offer a tool to solve a problem. If there is no problem, you don't need a tool. So making AI specific to something that is painful or that is time consuming makes it a lot more appreciated by the designers, by the engineers, by the end users. So it's really nice to see how essentially the perception of AI has changed over the years, how essentially the engineers have also learned that AI can be helpful, can be useful. It's not just a hype or a momentary trend.
Michael, how about you for feedback from customers?
So we work with every sort of major customer in the world doing silicon transceiver type design as well as digital, and certainly in the digital realm with Cerebrus, our AI tool in that realm, there are designs they can't do without it. But the digital realm has been relying on different computer applications or software applications for years, because when you're dealing with billions of transistors, you're not going to lay that out by hand anymore. So, but as the other systems get more complicated, they benefit from those solutions, and we're starting to we have customers who are benefiting from our solutions in the Virtuoso as well as Allegro space already, because like I said, with migration or just being able to do design centering, and it's good to produce a design. So I have a design that's working, and I'm getting ready to go into production, and procurement calls me and says, I can't get those SMD components you wanted from this vendor. I have to get them from another. So now all my models just changed inside my package design that my IC is sitting on. So I need to go in and rapidly change those models, which AI can do for me. I can put a new set of models in there, and I can just ask it to recenter that design for me, because now I'm going to production with a different set. So I think customers, like with simulation, when simulation got faster, people did more simulation. With AI tools, as they're going to be able to build pieces quicker, they're going to look at bigger, more complex systems, and they're going to look at other ways to trade off the design space.
Great. I'm going to go to some of the audience questions before we do these last three questions that kind of wrap up, what's going on in the future. So question about the MATLAB presentation: was the model used to extrapolate solutions outside the trained parameter space, or was it primarily used on the inside parameter space without having to do 3D EM simulation?
Yeah, so I'm going to give three answers because I presented three models. So for the first model, where essentially we use the AI model for the antenna, then the model is, how can I say, should be operated only within the range over which the characterization was performed. And in this particular case, we'd give a range for the parameters to be plus minus 15% around the design frequency of the antenna itself. For the second model, that was the one used for pattern reconstruction, then it is indeed, the model is used indeed for extrapolating the data. So we use only two orthogonal cuts of the pattern that represent essentially 1% of the total pattern to reconstruct the entire pattern. So that's almost by definition, reconstruction is extrapolation, if you like. And for the surrogate method, then the method essentially learns on the fly. And therefore, as it proceeds throughout the optimization. If an activation is triggered, then the model will run a new electromagnetic analysis to extend the surrogate model, reinforce the model, and then reuse it for optimization. So no, yes, it depends.
It depends. That's always the key engineering answer. And so next question, I think this would be for Alexander. So we want to know if they're using AI in creating measurement-based test plans for any of the instruments, if you know that.
Yes, there are solutions where this can be done. So we have the OpenTAD platform, which allows you to generate test plans.
Awesome. Looking at some other ones here. Do you have some documents for workflow automation using Python APIs?
Yes.
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 Okay, so they can find them on your website?
Yes.
There are also YouTube videos and all kind of white papers or presentations. I mean, depending on what exactly they're trying to do, I think a simple, quick reach out would be sufficient.
Awesome. Okay, and back to the questions that I had, what are some of the new things that you're working on with AI technology in your company? What's up and coming?
Do we want to assign someone or?
Oh, go ahead. You go first.
Okay.
Yeah.
So in our case, I think we in our presentation we've targeted some of the, let's say, goals. By end of this year, we actually aim to release the high power amplifier design automation to be open for the public, as we are currently working on ensuring that the results that we are providing accurate. And so this will be by end of this year, and we are also working on bringing like all the parts necessary for full front-end design, like mixers, switches, VCOs. So this is also currently under development. And yeah, also within the next years, we are also working on a deeper integration with Foundry flows. So bringing like more direct access to the foundries by means of the AI, and also working on partnerships which basically enable a full backend process for our customers. So from basically the AI design to the full chip delivery, basically.
And Michael, how about Cadence?
So we're certainly working to integrate these solutions into larger and larger problems. So when I'm doing, we're picking on amplifiers quite a bit here. The amplifier is more than just the IC, usually. I put it in a package, I put it in a system. Maybe I want to trade off my matching elements on the die or on the package. Maybe I want to, implement my inductors in the package rather than on the die. And I want a quick way to test that, to look at that. But also the AI or the simulation, it only understands what I include in it or what I tell it to include. So I have to start including bigger pieces of the package of the system for it to make larger improvements or be able to trade off different pieces of the system together. And that's one direction we're definitely going. When it would be great, let's say I can press a button and I can get an amplifier front end design, and I can go to a certain foundry and get that PDK. Now everyone can do it. So what is my value add as a company if everyone has the same solution? Now I have to get more creative in other areas. I have to trade off different packaging configurations, different implementations of that design. How can I distinguish myself now? So I think we're shifting creativity, as someone mentioned earlier, to different areas, as just as when we went from linear simulation to nonlinear simulation, we got more value, but then we had to do many more things, and now it becomes much more interesting to run designs closer to compression and things like that. So in one aspect, it's going to make our lives easier. In another aspect, we're going to have to be creative in another area.
And Alexander, how about Keysight, EDA?
Yeah, Michael already covered a lot of points. So the vector basically points to higher complex system. Power amplifier is just one building block in a larger system. So 3D heterogeneous integration, multi-physics, and everything which comes with it is the direction to go. every single piece impacts the RF performance. That always been the case, and that always been the problem. What we still see, kind of going back to the traditional workforces, that one engineer took care of a certain design step and then he handed it off to another one, and the other one ran another type of simulation, or looked at a different design aspect which was sitting higher in the system level stack, and he couldn't achieve his goal. Maybe the budget he had, or the space he had, or any kind of restriction given by the system level, he couldn't simply achieve. So we've seen traditionally that departments were fighting, engineers were fighting over certain domains to optimize the final system. So just doing one piece is not good enough going forward. And this is basically where AI is going to help, because it can just cover higher dimensional problems, like also what Georgia was saying. So all of those things need to come together. In addition, we are also very much aware of the domain we're operating in RF is very IP sensitive. So a lot of customers still don't believe in the clouds. They have hard metal on-prem solutions. So some of the AI technologies which you get as a customer, which I also use in my presentation, it's awesome. It's easy to use. You can just plug and play, but it operates in a cloud environment, which customers don't necessarily want to use, especially if you go to DoD, ITAR, or other, military or space defense people. They are very protective of the IP. So the solution we are focusing on are all tailored towards, being on-prem deployed ultimately, and being enabled to also run in air-gap solutions, so that people can actually design really high-performance solutions which give them the edge over their competition. To Michael's point, is like, what are you worth if everyone can do the same? And the answer is, your IP is what separates you from the rest. Your workflows, your intelligence you have in your engineering resources separates you from the rest. So protecting that is our key objective in everything we do with AI. And there have been plenty of examples just recently where, LLM chats have been leaked. Again, it's not the first time, and it happens over and over again. So supporting our customers and building on-prem trustworthy solution is key.
Georgia, how about MathWorks?
Well, I can't speak for the totality of MathWorks, to be honest, because MathWorks is doing lots of different things for AI, and MATLAB is used pretty much in every possible field of science and engineering. But talking about RF, I can tell you we continue to look at specific problems that can be practically solved with AI in meaningful ways. So we will continue on extending the use of surrogate methods to speed up optimization for expensive optimization problems, or for problems that have lots and lots of independent design variables or very large design space. RF, but also high-speed digital I/O, SerDes, mixed signal type of applications. That's definitely something we are investing, we are looking into. More on pattern reconstruction. So what I showed was about pattern reconstruction starting from two orthogonal slices, but then maybe you have a sparse data. We're also working on reconstruction of the phase, which means that you can speed up the characterization and calibration of large phase arrays, which is a big problem nowadays for MIMO application with thousands of antennas. So really applying AI as a tool essentially to speed up measurements in this case. And then, of course, we will keep on training networks so that users don't have to think about it and just use networks such as the one for antennas, just to use them out of the box. And because to be honest, I'm starting to think that the AI is not only changing the way we approach the problems, but also the way we learn about problems. I think the next generation in particular is really using AI as a tool for learning, not only for executing a job. So to get, say, I think that every single engineer, in large part, learn his job on the job, if you know. What I mean, trial and error, unfortunately, is a significant part of our training method. I think that AI can help and does help, and is a tool used by the younger generation to speed up this process of trial and error, understanding where the things work, where the things break. And I think that having these pre-trained models can really help this process of learning about new problems.
Great. I'm glad you kind of brought that up because I wanted to try to talk more in general about AI technology. Where do you see AI technology going in the next, 3 to 5 years, and what impact will that have on your work and what your company's doing? Anybody can jump in.
Maybe I take the first step at this. Just to add to what Georgia kind of was alluding to, is like we're trying to take the mundane tasks away, right? Automate those, add AI to this. At the same time, we don't trying to alienate RF designers by replacing them. We're trying to enable them to learn faster or to address larger problem spaces, right? So the problems are just going to expand further and further beyond just a single PA design. But right now we are still kind of in the trust building phase. We still have plenty of customers who have not invested in some of those underlying infrastructures. So GPUs are still expensive and they need to find ways to fund those. So those discussions continue. And in a 5-year term, I think you're going to see significant more efficient workflows. You're also going to see a change in the workforce where people have to not just look into a single problem anymore, but look about across the boundaries. Either they learn how to do this through those AI tools, like what Georgia mentioned is a great tool to actually learn, and also run trials and fail and do some more evaluations. And then you will see augmentation further and further in this domain. The long-term objective, of course, is agents, right, who can take care of most of this, and we basically turn into people who can drive the what is it we're trying to do rather than focusing on the how. So the how will be fully automated to a certain degree, but that also includes then the verification piece, the tape out piece, the hardware piece. So we always need to trust what we build, and that trust needs to build into the system. And that will be one of the biggest challenges. If you don't understand the system, how can you trust it?
I guess what I would add to that, if we're looking at 3 to 5 years, and I look at where industry is designing today, whether or not you think Moore's law is dead or not, certainly the electronics industry is trying to maintain that curve. And if we can't do it with a single process anymore, we're doing it with packaging techniques and more exotic fan-out techniques and interposers and mixing technologies. But there always this drive to improve costs. I mean, it's been there forever. So one of the ways to improve costs is to go to the most efficient manufacturing process we have, and that centers around CMOS. Digital, if anything can be done in CMOS, it's done in CMOS. And we see more and more of that, including more analog and more RF, as processes like TSMC and 6RF and 4RF come online. You see designers going to these smaller nodes. Smaller nodes have different manufacturing requirements. You can't just put particular lines out there. Now you have to worry about the lithography aspects, and you find you have these width spacing patterns. So you see more RF designers trying to include microwave and even millimeter wave designs into digital type processes, and so their design style is changing quite a bit. So how we help the engineer to move to that sort of new paradigm will be critical, at least in our business, and that's one of the aspects we're looking at to help have AI help us in that area.
Yeah, don't forget the statistics.
Well, yeah, we have many touched on statistics.
Yeah. So smaller nodes are increasingly difficult to control, right? So the variations are just increasing, and RF is one of the domains where that is a killer. So understanding those, managing those AI has capabilities of significantly augmenting engineers in that domain.
Oh yeah, 3 to 7 corners is you don't even think about something that small anymore. It's 27, 37 very large corner cases that you're going to consider or optimize around to try to get your design ready for manufacturing.
Anybody else on the outlook there? And so
Well,
we,
I think
Oh,
that
go-
less and less code is going to be, how can I say, manually written from scratch. I think that really anything that is going to be data analysis, visualization, reporting. I mean, let's not forget that nowadays a lot of the data sheets are still done manually by poor engineers. So I think that hopefully those type of tasks will be completely automated.
Yep, I did see a company selling like complete assistants now, not just agents. Multiple agents would make up, a workflow that they would completely automate for you.
Right.
So we've kind of talked about two things and the impact on the industry. One is, we've been able to use AI to design things for you, so you might need a less experienced engineer. It could be done by a inexperienced engineer because the AI is doing a lot of the development. But on the other hand, we've talked about how it's automating mundane tasks for the experienced engineer to do it faster. So I really want to know your outlook on, what impact do you think AI is going to have on the future engineers, RF and microwave engineers? How will their role change and the needs of their skills change?
Yeah, maybe I will add up here. So we think that AI will definitely remain a tool, basically, and but on the one requires skilled engineers to maximize its potential. So that means in the future, for example, or most probably, RF engineers will need broader interdisciplinary knowledge. That means not only in RF and microwave theory, but also in the AI-driven design methodologies and data analysis and complete system level integration. And engineers who can basically merge all of these domain expertise with AI capabilities will be the most valuable contributors in the future. And I mean, just consider, for example, within the last few decades, where engineers who were capable of programming developed tools like EDA or CAD software, which greatly benefited the entire industry. So the same applies now for AI.
Anybody else?
I would just add multi-physics here. So you may not want to just think about EE anymore, right? But if you look at mechanics and other things which are impacting the performance, if we keep pushing the boundary on performance, it becomes a multi-physics disciplinary. So engineers will need to understand, at least at a broad level, to drive those tools, what that means. So how electrons move is basically what we understand, but what about forces? What about temperature, fluid dynamics, and other systems? Those all come into the picture, and we're trying to add them to the AI augmented optimization challenges, so that we really can look at a full-fledged system and optimize the performance at every single system level.
And there's another audience question. In the future market, do you think there'll be like pre-trained AIs for companies, or custom AIs that each company will use, or do you think they'll use a product like from Rapid RF that's already done for them?
This is actually a question we get quite a lot, as we are providing right now a cloud platform, which is, as Alex also already mentioned, is not ETAC compliant. We've got this question already quite a lot, and yeah, this is certainly a step that we are aiming for in the future. But right now, let's say the greater audience and customer base is basically the one that we can attract with the platform, the cloud platform. But this is definitely a point where we are also trying to move to.
So let me answer this in that way. If you have two big companies who are currently competing in the same market, do you think they would want their IP to be available to the other company?
No.
So It really depends on what knowledge are companies willing to share. That will become a base model or foundational model. But everything else are basically tools which will need to learn within the refined and secured premises of those companies, because that's what makes them unique. This is their competitive advantage. If we take that away, we basically level the playing field and they have to redefine themselves, which is fair, right, to a certain degree. But that just means that the IP will move into a different layer, into a different direction. But there will always be the customization need for every individual company to be successful.
I guess I'll add to that there are companies that already have those agents inside them, very large companies that are doing this because they already have a phenomenal amount of design data and information that's all proprietary. And specifically when they're ahead of the game, they're ahead of everyone and leading. There's no information outside for them to get. It's not worthwhile to them. So they already have those on-prem, and they have those to help introduce engineers to the company, to introduce them to their design flow and their workflow. And so they can ask this AI agent a question before they even go to the next person. So EDA, we can do a lot, but I just look at some of the customers I work with in the mobile market space. I'm building my next level transceiver for 5G or 6G, whatever it is. I see design teams of 50 to 60 engineers building those transceivers. EDA companies are never going to have that knowledge, that domain knowledge, to be able to address that type of a design and all the problems. So those companies are going to be able to take what they've done in the past and build on that database. They're going to have their own internal AIs for a lot of these applications. I already see it.
Any other closing remarks? I think we've gone through all the questions.
It's an exciting time.
It is a lot happening. It's moving faster and faster every day. So this wraps up our first RF and Microwave Summit covering AI and RF. I'm sure we'll be doing more on AI next year. And we do have one in November on radar. So RF and Microwave Summit be November 13th. So watch out for that. So I'd like to thank all of our panelists here. You guys did a great job. I liked your presentations. Thank our sponsors, Rapid RF, Cadence Design Systems, Keysight EDA, and MathWorks.